Okay, Assalamualaikum and good morning, everyone. Okay, so today we will discuss your tutorial or assignment. So we have assignment 4, 5, and 6 to be discussed. So we will start with assignment number 4. Okay, so assignment number 4. Okay, so assignment number 4 is related to electromagnetism. Okay, so I think chapter 4. Okay, so automatic external defibrillator AED is used to re-establish normal rhythm of the heart with arrhythmia. So arrhythmia is when your heart, the electrical signal in the heart doesn't produce periodically, or maybe it is produced not regular, irregularly. So it causes your heart to beat not constantly. Maybe the rhythm is not as normal people. So we use AED to treat arrhythmia. So consider the idealized geometry of the abdomen and a spherical heart with 2 AED electrodes. So the active, the top one, and the ground is the bottom one for defibrillation procedure as shown in figure 1. Okay, so this is the figure. So you have abdomen, the rectangle, and the spherical heart. The electrode is a square of dimension 10 by 10 cm, and the heart is a sphere of radius 5 cm, in which the location is shown in figure 2. The conductivity of the abdomen and the heart is 1 Siemens per meter and 0.05 Siemens per meter respectively. So question A, simulate the defibrillation process by following this step. So develop the geometry and then define the global parameter D equals 10 cm. And then use suitable physics and boundary condition. Use final mesh for the heart, normal mesh for the rest of the geometry, and compute using stationary study. Okay, so firstly, we can start by choosing model wizard. And then this is a 3D geometry. Okay, so we choose 3D geometry. And then this is electromagnetism. So it's a AC/DC, okay? AC/DC and electric currents. And then the question asks you to use stationary. Okay, so we can start by first drawing the geometry. Okay, so firstly, we need to define the global parameter. So the question asks you to define global parameter D equals 10 cm. So here in parameter, just define D, 10 cm. So this D will be used in drawing this geometry. So the D is here. Okay, so we draw the ground electrode using D. So let's draw this first. So in the geometry, we can start by drawing the abdomen, the rectangle. So the height is 40 cm. And then, the height. And then the depth, I think 20. And the width is 30. So try build. Maybe we change this. Okay. So we get the abdomen. Now we can draw the sphere. So the sphere is located here. So maybe we can start by taking the sphere. So the radius is 5 cm. So position originally here. So you need to move it 20 cm from origin. Okay, 20 cm from origin in y direction. Then 25 cm in the z direction. But it's still outside, so you need to move it in the x direction, 10 cm. Now the heart is inside. Then we can draw the electrodes. So we start by drawing the top electrode. So we need a plane. So we need to draw the electrode on the frontal plane here, on the front plane. So it's a ZY. So by default, it's at the back. So move it forward, okay? So change the distance. And then we can okay. So di pandangan sini. So we need to draw the electrode here. Okay, so I think the step is similar to the one in slide. Okay, so whichever way you draw, as long as you get this correct, it should be okay. Okay, so we go back here. And then so we can see that okay, silap ke sini pula. So kena anjak dia sikit ke sana. Okay, and then we need another work plane to draw this ground electrode. So just duplicate, and then the plane is here, ZX. And 30 cm. So we have electrode here already. So let's go to the electrode. So by default, it's here. So we need to change the Y. And then the height is D. So we just put D here. Okay, so by default, it's 10 cm. But this is measured until the center. So the 10 cm is actually measured from here until the edge, okay, the side of the electrode. So we need to adjust a bit. So D now it measured from here until the center of the electrode. Okay, so instead of using 10 cm, so you use D instead. Okay, here you use D, you don't use 10 cm. Okay, so now we have the geometry. Then we can set the physics first. So here in the physics, we need to set the conductivity. So by default, the software gives you only one current conservation. So you need to add one more. So just duplicate. Kita boleh. Okay, so just duplicate, and then in this second current conservation, you just select the heart. Okay. Okay, so just scroll your mouse, so you can get the heart. Okay. And then the heart has electrical conductivity equals 0.05. And then go back to current conservation 1. You will see that it returns here overridden. So overridden means the domain number 2, which is the heart, is not going to have similar properties as current conservation 1, but it follows current conservation number 2. Okay, so in the number 1 here, we just set conductivity equals 1. Okay, so now we set the current conservation, conductivity. Then we need to set the ground and active. So right click, choose ground, and choose the bottom electrode, and then right click again, choose normal current density, and then just write this thing. Then set on the top electrode. Okay, so I think everything has been set. Then we can mesh. So to mesh, So by default, it will mesh everything at the same time. So we want the heart to have finer mesh. So right click and choose free tetrahedral. So free tetrahedral is for 3D. Okay, so we have other things like triangular. Free triangular is for 2D. And we have edges. The edge is for 1D or only lines, okay, garisan. So we choose free tetrahedral. And then in the geometric entity level, instead of using remaining, we choose domain and select only the heart. Okay, so again, scroll your mouse. So we only mesh the heart, and then right click the free tetrahedral, choose size, and then in the element size here, you change to finer and try build. So the heart is mesh in this way. Then try bit all. Oh, tak boleh. So again, right click, choose free tetrahedral, remaining, and then size normal. So remaining here means the other geometry. So try bit all. So if you can see that the heart has a smaller mesh compared to the rest of the geometry. And now we have everything. Then we can try compute. Okay, so the simulation has finished. Then we basically you have done a question for part A. Okay. Okay. Any question before we move on to the analysis? Okay, so we look at question B. So plot the distribution of electric current density in the heart and remove other unrelated geometries. So there are many ways you can do this. So some students, some of you do some other things that I never know, okay? But I only know one way. So one of the way is you got solution, and then selection, and then change domain, and then choose the heart. Okay, so now solution one, study one, solution one, number two here, will plot only the results on the heart. Okay, and then this one can be disabled. We don't want this. So right click results, 3D plot, and then change the data set to number 2. So we get the heart only. And then the question asks you to draw the distribution of electric current density. So here, right click, choose maybe volume, and then go here in the expression, and then in the electric current, choose current density. I think it's here. Current density. Nope. Ni ke? Electric current density. Mana dah? Current. Nope, not this one. Electric displacement. Maybe this one, current density norm. Okay, so you get something like this. Okay, so you plot only the heart. Okay, so basically if you plot this only the heart, then the answer is correct. So if you plot something, even though you plot the heart, but there's still the abdomen, maybe deduct 1 mark macam tu lah. Okay, so we get question number B. And now question C, determine the average electric current density in the heart. Okay, so this one, you need to do averaging. So here in the derived value, right click, choose average and volume average, because the heart is a volume. Okay, it has a geometry. So then again, choose the heart. And then in the expression, just look for electric current density. And then evaluate. So this is the electric current density, average electric current density in the heart. Okay, 8 markah. Okay, now we move on to question D. So the placement of the electrodes is important to produce adequate amount of electric current density flowing through the heart, which is below 14, okay, in order to avoid shocking hazard. So repeat the simulation in A by varying the electrode placement of ground electrode using parametric sweep D equals range, this range. So we can go here in the study, right click and choose parametric sweep. So in the parametric sweep, you just add D that we have defined earlier in our global parameter. And then just write range starting from 5, 0.5, 30. So the unit cm. Okay. So I think that's it. And then we can try compute. So it will take some time, or it might get error. I'm not sure, because last time I think there is an error. So the simulation might take some time. So itulah, okay, kena bersabar. So make sure when you want to do the test tomorrow, just make sure you close everything in your laptop, like Google, PowerPoint. Macam ni banyak banyak benda yang tak perlu. So tutup, okay? Tak bergerak. Okay, sekejap So I think I know why last time student can answer ada something salah. So maybe I think the range kot. Okay, lama gila. Then we finish question D1. Then disable this first. And then we can go to D number 2. From the simulation, determine the average electric current density in the heart for each electrode, ground electrode position, and plot the graph of the average current density against D. So again, this has been done in question C. So it's the same thing. So you just duplicate this. And then here, just select this parametric solutions. And then try evaluate. Okay, so you will get a series of values for different D and the electric current density. And then from here, the question asks you to plot graph of average current density against D. So in this functionality, you just click this button, table graph. So you get a graph automatically plot for you, current density versus D. So then the question asks you to estimate the maximum D before the current density exceed the hazard limit. So the question says hazard limit is 14. So it's somewhere here, 14. So the maximum D value is about 15 cm. Okay, so you cannot exceed D more than 15 cm. So if you exceed D more than 50 cm, then the current density in the heart becomes more than 14, okay? More than 14, which exceed the hazard limit. So you can answer the explanation when you save or export the report later. So in the report, I think so not here. I think you can save in intermediate. Okay? So maybe if you save in intermediate, so save in Microsoft Word and then browse. So the Microsoft Word, later you open the Microsoft Word and put your explanation. What is the value of D, maximum value of D before the current density exceed hazard limit, and write the reasons based on the graph. Okay, so you can write in the Word, okay, in the Microsoft Word. Okay, so that's it for assignment number 4. So we have 2 more assignment. So any question for assignment number 4 before we proceed? Okay, so we proceed to assignment number 5. So assignment number 5 is about solid mechanics, okay? So the mechanical property of a myocardium wall can be modeled using 2-parameter Mooney-Rivlin hyperelastic model, where the strain energy density W is defined as given here. So C1 and C2 are material constant defined in table 1. The diastolic phase of a left ventricle can be simulated on a 2D axis symmetric by applying an internal pressure from 0 to 7 kPa. The upper boundary base of the LV is fixed in all directions. So simulate the diastolic phase of LV by following this guideline. Okay, develop the LV geometry and then define the model using appropriate physics, define the parameters, set appropriate boundary and initial condition, and use parametric sweep. So let's start by choosing the model wizard. And then the geometry is in axis symmetric, 2D axis symmetric. So you choose 2D axis symmetric. And then this is a solid mechanics problem. And then it's a stationary study. Okay, it doesn't involve any time, no time given. So we choose stationary. Okay, so we can start by drawing the geometry. So here it is ellipse shape. So we can draw ellipse. And then the first ellipse, we draw the outer one first. So the outer one has, I think this is A axis, 7 cm. And the B axis, 3 cm. Okay, tukar balik. And then we draw the inner ellipse. So just duplicate. So the inner ellipse is 2 cm here and 6 cm. And then enlarge. So we want only 1/4, okay? 1/4. So we can draw square. So the square, the first square will cover the top half. So change the position. So maybe negative 0.04, for example. So it covers the top half. And then another square to cover the the third quarter here. So change the position. Change the position so that it covers here. So maybe make it small. So we move it here. So negative cm. Tujuh. Macam cover sini. And then ke bawah negatif 7 juga kot. Okay. And then you can choose Boolean operator and difference. Okay. So we get 1/4 of the ellipse. Okay. So garisan ni abaikan, tak ada apa-apa. And then we have developed the geometry. Then we define the model using appropriate physics. So here in the solid mechanics, so it's automatically highlight the whole LV, left ventricle. And then we need to set this Muni-Rivlin hyperelastic model. So right click material model and choose hyperelastic. And then here in the material model, choose given 2 parameter, okay, given in question 2 parameter, and then change the parameter value. So maybe just name it C1 and C2. We can define a parameter. C1 equals 3 kilopascal and C2 equals 5 kilopascal. So go back to the hyperelastic material. So you will see that this becomes black. Just now it is yellow in color. And then the bulk modulus, maybe we put KB for example. So define again in parameter. KB equals your matrix number. So in my case, I give example this one, okay, kilopascal. And go back. Then we need to set the density. So density, it's maybe we define rho. So go to parameter and write rho. So this is in SI unit. Don't have any like kilo ke centi ke. So just put number, should be okay already. Because later in here, the unit is already given here, kilogram per meter cube. Okay, so we have defined, accidentally defined the parameters, but we haven't finished defining the boundary conditions. Actually, physics pun dah define. So we need to define boundary conditions. So the question says the upper boundary is fixed. So we choose boundary fixed constraint. So choose the upper boundary, this one, the upper one. So fix in all direction, you cannot move. And then use appropriate mesh. So mesh, if you use normal mesh, it's quite big actually. Okay? But if your computer is good, okay lah. Okay, I think maybe use coarse good. But if you think your computer can run faster, use normal. So that's why it doesn't specify which mesh type. Okay, and then we need to define the boundary load. Okay, sorry, we haven't defined the boundary condition yet, the boundary load. So the question says applying internal pressure. So internal pressure apply here on this load, boundary. So maybe we can, again, in solid mechanics, choose boundary load. And then change here to pressure because we are applying internal pressure. So choose the internal boundary. And then the pressure is changing, okay, because we use parametric sweep. So maybe we choose, we write load here. And then we define in the parameters load. Okay, so we define as 0 first. Later we will change this load at parametric sweep. Similar to previous assignment, we change the distance of electrode using parametric sweep. But this time we change the load using parametric sweep. Okay, so here is the load. Then we can go to study and choose parametric sweep. And then add, choose here load, our load just now. So it's in Pascal, which is okay. So we write the range starting from 0, increased by 10 until 7,000. Okay, 7 kilopascal. I think that's it. Then we can try compute. Okay, so finish the simulation, then we go for the next question. Plot the three-dimensional 200-degree revolution for the LV total displacement and deformation. So firstly kita tutup satu ni dulu. Terlalu banyak benda. Oh, actually we want the second one. So we close this. So here, the question wants you to plot the 3D plot. Okay, even though the question is 2D axisymmetry, so we want the 3D plot. Because so this is the 3D plot, but the angle is not 200 degree. So we can change here. So first 5, so this is 5 kilopascal, okay, silap. So 5 kilopascal. And then okay, so to change the degree, I think it's here, revolution 2D in dataset. And then so here at revolution layer, so we start at 0 until 200. And then go back here and plot. Okay, so this is your plot. And then this is the von Mises stress. So we don't want von Mises, we want the displacement. So go here and change to displacement. Okay, so this is the displacement, and by default, it also plot the deformation. So in case if your console doesn't by default produce this deformation, you can just right click on the surface here, and there will be a selection for deformation. Okay, just click that one. So this is for question B. And then question C, calculate the internal volume of LV for all time step. Use the formula volume equals integration of negative pi and r squared times dl. So integration dl here is the line integral. So what you need to do is here in the derived values, right click, choose integration, and we choose line integration. And then we want the volume, the internal volume. So we choose only the internal line. And then to calculate volume, we need to write this equation in the expression. So just write negative NR. I think it should be NR, but later we'll see. Times R, okay, or times R squared. Okay, so tak ada. So not NR. So I think it's small n word. Okay, so small n. So check the unit. So unit is meter power 4. So meter power 4 is not volume. So volume is meter cube. So you need to do something to adjust something. So actually you need to change this compute integral. So just untick, okay? And then click evaluate. Okay, so you get a table here. And then the question asks you to plot the internal volume against pressure. So just click this table graph. And you get the plot. But the unit here, the name is not correct. So you need to change this. So to change this, I think you can go to oh mana ya? Lupa dah. Okay. Go back here. Boleh tukar kot volume. Tak tukar, okay, tak apalah. But actually you can change the name, but I don't know where. So this is the plot that for question C. Okay, so when you apply pressure, apply load, the volume is increasing. It doesn't show any sign on reaching steady state value. Okay, so this is for assignment 5. And last one, assignment 6. Okay, so assignment 6 is about fluid mechanics, CFD. So a fusiform aneurysm occurring in a blood vessel has a risk of rupture, which could lead to uncontrolled bleeding. So aneurysm is commonly occur in brain. So most of the time, if maybe older people, maybe some of your datuk nenek ke, maybe got stroke. So most of the time, the occurrence is because of aneurysm. So aneurysm it's like the blood vessel becomes macam form a balloon, okay? Dia macam keluar macam benjolan, ya, macam ada balloon. So it ruptures. So when it ruptures, then blood comes out from the blood vessel and boleh menyebabkan kematian lah, lead to death. So consider the idealized geometry, 2D axis symmetry geometry of a blood vessel with a semi-spherical aneurysm shown in figure 1. So the inlet pressure is this formula, and then the outlet pressure using Winkelcell model. And then in addition, the outer wall of the blood vessel is assumed as no slip boundary condition. Assume that the viscosity and density. So simulate the blood flow. So first develop the geometry. So firstly, we choose model wizard and axis symmetry, 2D axis symmetry. And then we choose laminar flow. Then we can choose time dependent because this one has time. So time dependent. Okay, so we draw the geometry first. So this geometry, they draw horizontally, but your console, it's vertical. Okay, so you need to draw this vertically, okay? So start by choosing a rectangle. So the height is 30 cm. And then the width is the radius 10 mm. Sepatutnya dia kena jadi menegak, okay? And then we draw the spherical here, the circle here. So circle. And then firstly change the position somewhere in the middle. So somewhere in the middle, maybe about 15 cm in Z direction. Okay, so the radius is 30 mm. But here, the question asks you to define radius in global parameter. So we go back to parameter. So define radius. So use 30 mm. So here in the drawing, instead of writing 30 mm here, we use radius. So this one, the center is on the other side of this rectangle, okay? But this one in the drawing, it's on the red line here. So we don't want on the red line, we want on the other side. So we move the position 10 mm, okay? Okay, kita nak kat sini. So now we have some extra parts here. So we want only this. Okay. So we need to do some adjustment, Boolean operation. So maybe we can let me draw rectangle, a square. So on the other side, okay. So we bring -1. Okay, so we delete this part of the circle. Then we choose difference. So we want to add this and this, and we don't want this. Okay, so we get this. So at this time, don't worry about the inside circle here. The most important thing is that we have this bulatan di luar. I think it should be okay. Okay, don't worry about the internal things, as long as we have this circular shape outside. Okay, and we don't have anything beyond the left side of the red line. Okay, kalau ada something on the left side, when you rotate revolution nanti, it will be something else lah. Okay, but I think because console, it will automatically delete anything on the left side. So you basically you don't have to perform this difference pun tak apa. I think should be okay. Okay, fine. We have drawn this. Then we can use suitable physics, space dimension. That lies. Okay. Okay. Dia beritahu ni, warning ni bermaksud dia remove anything on the left side. Okay. So warning, nothing happened. Okay, don't worry. So we set the physics. So firstly, we need to set the wall. Okay, the wall is correct here, and then as is symmetric, this part, and now we can set the inlet and outlet. So we start with outlet. No, inlet first. Outlet macam susah. So maybe we set inlet here. And then we want pressure. So pressure. Maybe we can write here P inlet. Okay, P in. So we need to define P in somewhere. So here we define in definition. So we define P inlet. So the P inlet has this equation. So I think in slide already gives to you how to write this. So if the time is less than 0.5 second, then P inlet equals 120 times sine times 2 times sine 2 times pi times t. So you need to divide by 1 second. Divide by 1 second. Close bracket. And then if t bigger or for other t, P inlet equals 0. Okay, so make sure you don't have any yellow color. So make sure it's all black. Indicates it's correct. So here in the inlet, check again, then it's also becomes black. Now we can set the outlet. So the outlet needs to follow Winkelcell model. Okay, to be honest, saya tak ingat apa dia punya code. So kena refer nota. So we can write here P outlet. Okay, and then we have yellow colored P outlet. So we need to add another physics. So add physics, global ODE and DAE. And then here in the global equation, so you just follow the one in slide, okay? It should be the same. So firstly, you need to define C and R. So in the parameter, C equals 2.75 cm cube per meter curie. And then R. So you cannot use R because in console it's reserved variable. So maybe use R1. So 1 millimeter mercury times second over cm cube. Okay, so go back here to global DAE. So follow from slide. So name P out. And then C times P out. Double T. Make sure you have double T there. And P out over R1 minus Q. We don't have Q. And then in the unit, change to Pascal. Change to the Q. Then we need to define Q somewhere in the variable as well. So variable. So we need first integration. So integration coupling. And then integrate boundary. And then uncheck compute integral. And then in the variables, Q equals entropy1 2 times pi R times W. Make sure you get meter cube per second to represent the correct unit of Q, which is flow. Flow is volume per second. Okay. And then here in the global equation, so everything will turns out to be black, okay, which is correct. So just now it's yellow. And then check again anywhere else if there is any yellow color. So no more. Then we can go to computing. So use bigger mesh. Okay, so firstly use bigger mesh. So by default it's a normal mesh. Okay, sangat halus. So try use coarse or maybe coarser. Okay, depends. Okay, I think it will take long time, but the result will be kind of inaccurate. Okay. Okay, then we go to study time dependent, change the time range. Okay, so we don't have to change. It's actually follow the range given. Then we can compute. Oh, tak define. Okay, so we don't define mu and density. So density, rho, and mu. So we need to define in parameters. Rho, 1000, and mu, 3.5 millipascal. So go back here. Then we can compute again. Oh, dah pukul 10. Tak apa, sekejap lagi. Okay, so we turn off this first. So we want this 3D. To question B, to answer question B, we need to plot the velocity field at 230 degree. So similar to previous question, change the revolution angle 230, and then in the velocity, change the time to 0.6 second. So we get this velocity. And the question asks you to describe the velocity pattern in the aneurysm. Okay. So nak describe apa ni? So maybe you can write in the Word document. If you look at the aneurysm, most of the aneurysm part is blue color, and only some which is near to the boundary of blood vessel, there's some green color or light blue color. So maybe you can say that the fluid velocity, the fluid maybe has velocity inside the aneurysm part that is nearer to the main blood vessel, but at the part further from the blood vessel, the velocity is almost zero. Okay, so just write anything that you think that describe the patterns from the results. Okay, janganlah describe benda lain. Okay, color biru, ni color hijau, color tak adalah, dia nak pattern. Okay, so that's for question B. And then question C, determine the maximum wall shear stress. So here in the derived value, again, right click, choose maximum. So because this is I think 2D, so we choose 2D surface. So select everything. And then at time 1 second, so choose the last time. And then the expression is given to you. So you just write mu times, so this is shear rate. We can find here shear rate. So this is shear rate. So you need to times mu. So when you times mu, you get the wall shear stress. So shear stress is in Pascal. So this is correct, in Pascal. Stress, okay, stress in Pascal. Then evaluate. So this is the maximum wall shear stress at time 1 second. Okay, now we move on to question D. So D1. So we need to use parametric sweep. So right click, parametric sweep. So add radius. So just write range here 40. So it's in mm. And compute. So you'll take longer time. Okay, so we have finished question D1. Then we can go to question D2. From the simulation, determine the maximum wall shear stress for each size of aneurysm at time 1 second. So this is similar to question C. So just go back to surface maximum here and duplicate, and then change the data set to parametric solution and change the time to last. We want the 1 second, and then evaluate. So just create new table. So we get this result, and then plot the graph of the maximum wall shear stress against radius. So just click this plot table graph. So we get the results of something, shear stress against something. So the something here, you need to change in the x-axis data, choose radius, and try plot again. So there are two plots here. Okay, so we plot shear stress against radius. And then the question asks you to describe the effect of size of aneurysm on wall shear stress. So here, when the aneurysm is bigger, then the wall shear stress is reduced, okay, becomes lower. So actually, in real life, when low shear stress exerted on the wall, actually, the lower shear stress, the higher chances the aneurysm can burst. Okay, so maybe we thought that higher shear stress can cause burst, but it's the other way around. There are many research that actually found this. So smaller shear stress can cause higher chance, yeah, or more risk of rupture on the aneurysm. So bigger aneurysm radius has bigger chance of rupture, and it is shown by the lower value of shear stress, wall shear stress. Okay, so that's it for the tutorial. Sorry for delaying until 10:15. So any question before we end this lecture? So tomorrow test is at 8 a.m. as usual until 10 a.m. So similar rules like last time. If you submit late after 10 a.m., so this time 1 minute, 5 marks is deducted. Okay, so do not submit late. And if your simulation you think it will take some time, then make sure you use bigger mesh. I think it's indicated in the slide, in the question later. Use appropriate mesh or something like that. So try to use appropriate mesh, and please understand about how to use parametric sweep and how to implement the parameter. Okay, so draw the geometry using parameter. So similar type of question, similar kind of question, you need to simulate and then plot something, and then parametric sweep and then plot something and describe something. Okay, so that's it for today's class, and good luck for your test tomorrow, and see you again in your project presentation in week 15, inshallah. Assalamualaikum. Goodbye.
Doktor,